Okay, so let us get started. So today we'll be seeing variants of the VAE. So in the past few sessions, we have seen what are latent variable models, and we have seen what is what is a variational inference using a variational distribution, which is used to estimate the distribution uh, of the latent variables, posterior of the latent variables. Anyways, so we have seen that a VAE has two objectives or two terms in its objective. The first term is a reconstruction term. It's reconstruction plus scale divergence, right? So the scale divergence minimizes distance between the distribution of latents and the normal 0-1 distribution. Why the normal 0-1 distribution? Because we want to, at the end of the day, sample from the normal 0-1 distribution and then use our decoder to get outputs. So if you've followed the first few sessions, we have seen this in great detail, that the architecture goes as follows. You get like an input X, you pass it through a encoder, which models the mean and standard deviation of the data. You do reparameterization. This is called reparameterization. So in reparameterization, you convert it into a normal mu sigma random variable, and q of z, q phi of z given x is normal with random variable z, q phi of x, and sigma square phi of it's a diagonal matrix. So we say that the latents are independent. So if you have a multidimensional Gaussian with the diagonal elements to be non-zero and everything else to be zero. So this tells that there's no correlation or covariance across the random variables, which in Gaussian case means independent. We've seen that in previous courses, and that's what is known. So the random variables, the latent dimensions are independent. So once we get this, we sample from this distribution and we pass it through a decoder, and we get a reconstruction term. And that's the first term that we have over here. So the second term is the scale divergence term. It tells that this should go towards normal 0-1, as I have been reinstating multiple times, so that when you sample z from normal 0-1, p theta or m theta of z is a sample. M theta of z should be distributed from the data distribution. That's the idea. Would be close to the data distribution. That's what you're trying to model. So we should be able to get data. This is generation. We'll be seeing all this today, and we'll try to understand each of these. We'll see the implementation of a VAE as well. So we have a latent and we have the data that is being modeled using the latents, right? So now we have seen that the scale divergence term is this. We derived it last time between two normal distributions is given by this sum where squares of means and variances, and this is log term. Okay, so that's fine. So what we'll today do is we'll study a few variants of this VAE. We'll study what is called the beta-VAE, which is what we'll also implement, and we'll also study what is called the info-VAE, where we'll see how the vanilla VAE has some limitations, especially in the generative, how crisp the images can be, and these models generally give you better reconstruction or better images, maybe crisper. So while let's start with a normal, start with a thought experiment. Say q phi of z given x almost becomes equal to normal distribution. So, and it becomes, not only does it become to very close to normal 0-1, which we actually want it to be, we also see as it goes towards normal distribution, this sort of becomes sort of independent. It becomes q becomes similar to q phi of z, which means independent of the input. starts to become as the scale divergence between data and or latent distribution and the normal 0, 1 distribution decreases, the latents corresponding to different data points come closer, making reconstruction a difficult process, right? It makes reconstruction extremely difficult. So let's see, why does it make it this difficult? So let us consider you have two data points, x1 and x2, right? Which could be very different in character, or features. So to be exact, let's say x1 is from the MNIST dataset, and say x1 is 7 and x2 is 4. So they have different features corresponding. It's this digit. It's an image of the digit 7 and image of the digit handwritten digit 4, right? So maybe when you are training this VAE, you will get a distribution like this: q phi of x given, or rather q phi of. So this is a normal distribution because we model the mean and standard deviation. And this as q phi of z given x2, right? So now, as scale divergence between normal 0, 1, it becomes very close to one another. So now say the normal distribution is like this. This is normal 0, 1. So what would happen if the scale divergence between these two it decreases? So it will create an attractor between these two. So these two distributions, distribution 1 and 2 would come, 1 and 2 would come close to one another. So what would happen if these two comes close to one another? Now there's a very difficult situation here. So this is the thought experiment. This is the dilemma between reconstruction and separation, that is ability to generate. So if you are close to normal 0, 0, 1, you will be able to generate better, because you are sampling from, because the model has been trained to reconstruct from normal 0, 1, and you are sampling from normal 0, 1 during generation or inference. But you will not be able to reconstruct, is what I'll tell you. Why will you not be able to reconstruct? Is because of this problem. So say these two got very close to one another. So what would happen is, say a new data point x tilde comes, and x tilde is very similar to 4. Say it's a tilted 4 like this, right? So now, although see, if they are very close to one another, the chances that the x tilde is represented somewhere here, or say somewhere here, x tilde is represented somewhere here, increases. So this is q phi of z given x1 and q phi of z given x2. Right. So now what would happen, you can see, is under the Q distribution. So if you consider these two distributions to be the canonical distribution of a 7 and a 4, so they say, so you will see that q phi of z given x tilde, this is say under, so we'll say this is distribution 1 and this is distribution 2. So if what I mean is, if you pass for distribution 1 and 2, so this is most 7s are class, most 7s have this distribution and most 4s have this distribution. So you can see that the q phi of 1 is clearly greater than q phi z tilde of z of x tilde under the second distribution. So which means the latent, there is a chance the latent looks more like a sevens latent. Therefore, when a p theta of x given z reconstructs the data, it will reconstruct it more like a 7. Because we can clearly see that this probability under the first distribution, which is the 7's canonical distribution, is having a higher probability than this 4's canonical distribution, although the data comes from the 4's distribution. So as you can see, if in the worst case, what would happen is if everything becomes normally distributed, all of these would be overlapping, and then you would have no reconstruction. If KL between Q phi of Z given X and normal 0, 1 is 0, and Q phi of X given Z becomes equal to Q phi of Z, which is equal to normal 0, 1 now. So if these two things happen, they become independent. The latents become so highly overlapped that they become independent of the input. So this leads to poor reconstruction. So now what can I do to prevent this from happening? So I can do something called as a beta-VAE. So if this happens, if the KL divergence end up having a larger weight, we have clearly seen from this example here that we do get bad reconstruction. This is the example that you should keep in mind. Right? You get bad reconstructions. So now we'll see what we can do to prevent this bad reconstruction from happening. So remember, what is p theta of x given z? What is it distributed as? You have the latent, and we have this decoder that in the VAE, the decoder which tries to decode the data from the latent. So I'll just draw the decoder once. You have a latent input, which this decoder takes this input and outputs a distribution of the data. So what would you expect, or what have we shown this to be? We have shown that this is normally distributed. We model this as a normal distribution, where the model, say the p theta is being modeled by m theta, which is a neural network, is the mean of the distribution. We try to model the mean of the distribution given the latent, and we say we have a constant. So in our case, we said that it is a covariance of half. So what does it mean? So when we do the log likelihood, we get this term in the reconstruction term, this becomes equal to the log of. So there are some constants because you remember any random variable normal mu sigma is given by 1 by 2 pi to the power dimension by 2 half e to the power or exponent of minus half x minus mu transpose sigma inverse x minus mu. Right? This is given by this term. So now I can remove, when I take a log, this term just becomes an additive constant without any learnable parameters. So I'll be using, when there are some constants without learnable parameters, I will be using this plus c sign to show that. So only the second term has some learnable parameters. So this is, in our case, is x minus m theta of z. We have, so then since this is a diagonal variable, so the sigma is equal to, what is sigma? Sigma is equal to half dot, everything is half, right? This is what we have. So you will end up having sigma inverse, which is comma 2, 2, 2, and so on. So you will get x minus m theta of z, right? This is the expression. So sigma inverse is, since it's a diagonal matrix, is just the inverse of all of these. So you get a 2, 2, 2 matrix. When you get that, what does happen? You get minus half, as we have seen before, x minus m theta of z, and you weigh each of these terms. This is L2 norm, since it's x transpose x, and we have a diagonal matrix D. We know this is equal to, this is, if it's a diagonal matrix, we know, and each of these terms are also the same. We know that. We have shown last day if the diagonal matrix is D1 dot 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 DZ, or D, if you have, let's write it sigma 1, sigma 2, and sigma D. So it's just like weighing. So x transpose x is the summation of xi square. So if you just had x transpose x, this is the summation of xi squares from I equal to 1 to D. Right? This is just a L2 norm. It's the inner product of the row vector of x1, x2 dot dot xd, and this is x1, x2 dot dot xd. So you can see if you take an inner product, you get the squares of each term. It's just the distance from the origin multiplied by, if you have this diagonal entry, if you, since linear algebra is, you all are familiar with it, it's just weighing each of these x1s with the sigma 1 term. So this is sigma 1 times the square. So here you have all of them to be 2. So I can just tell you, you can take 2 common and you can have the reconstruction term, which is the distance between the actual data and the reconstructed data, into 2. So you get this as the objective. This is the reconstruction objective, which you maximize. You say this is the reconstruction objective. So now you're saying that you're not getting better reconstruction. If you're not getting better reconstruction, what are you going to do? So if you're not getting better reconstruction, there's a way you can guarantee that. What you can do is you can make this variance that you have very, very close. So you can say that I want perfect reconstruction. So I would only be, I have a control over the variance. If the variance is smaller, if I can shrink the variance somehow, I would be able to make better reconstruction. So what do I mean by that? So since without a half, say I model p theta of x given z, right, as say normal x m theta of mz. So this is the beta-VAE. And I'll show you why we do that. Beta by 2 half into beta by 2, right? So instead of a 1 by 2, I multiply a beta. Beta is a hyperparameter, which gives you best reconstruction and generation. Okay. So this is the hyperparameter that gives you best reconstruction and generation. What do I mean by that? I mean that if beta is small, if beta goes to 0, right, my variance for each latent should go to 0, which means my distributions would be something like this for the data. And this would decrease overlap, right? It would decrease the overlap between data. And what would end up happening is that if I would get perfect reconstruction. So if this was your Q2 distribution akin to 7 and Q1 distribution akin to 4, or rather 1 and 2. So you would never encounter a place, you would get better reconstruction. Because the latents, or because the reconstruction term is forcing, you'll get better reconstruction because the reconstruction term is forcing the mean of the data to be exactly same as so the mean of the data, the mean of the reconstructed data, you should say, mean of the reconstructed data to be same as the input. Because we are minimizing the variance between, we are reconstructing the term, we are having this reconstruction term, which is making Z equal to the model learning a Z such that, or learning a reconstruction that will make it equal to the data X. This is the data input data X. So if you're making the latent specifically equal to the latent, and you're saying that there is no variance in the data, if I make beta to be very, very small, then you're inadvertently, what are you doing? You're saying that your data may be somewhere here, your data may be somewhere here, and your p theta of x given z may be somewhere here. So if this was input data, that and you could model the p theta of x given z in this form, right? You could just say that you very closely. Initially, you could have, so if you had a large variance, you could have a thing like this. You could have a larger variance where this is your x and this was your p of x given z, right? So you are saying that I don't want this variance, I shrink the variance. If I shrink this variance, I get better reconstruction. So let's write down the loss function then for this. So then this becomes in the same way, log of exponent of minus half. So your sigma inverse matrix is 2 by beta into the identity matrix, right? So whatever we had here, we just invert the scaling term. So we'll have x minus m theta of z transpose 2 by beta x minus m theta of z. So 2 and 2 gets cancelled. You get 1 by beta x minus m theta of the latent squared, right? So this is what you end up getting. Great. So what does your loss function look like? Your loss function of beta-VAE looks like 1 by beta x minus m theta of z squared minus the DKL term of q phi of z given x and normal 0, 1, right? So now what will I do? This is equivalent to saying x minus m theta of, so if I multiply a constant throughout, the loss functions would have the same minimum value because this is so we have discussed before, a constant into fx, the argmax is the same as argmax of fx, right? Because if I have a matrix like this, x squared, a c times x squared is also going to be the same. So if c times x squared, cx squared, this is x squared, both of them will be the same, will have the same minima, same extrema. So both maximum and minimum, if you multiply a constant, would have a same value according to which the function minimizes or maximizes. That's the idea. So it is equivalent to saying this is equal to DKL q phi of z given x and normal 0, 1. Right now you see if beta is small. So we started off by saying that I want perfect reconstruction. There shouldn't be. So I started off with, so see the beauty. Started off saying if my data is here, I want something like this, the p theta 1 of x given z to be this, and not p theta 2 of x given z. So here, beta for theta 1 will clearly be less than beta for theta 2. because I want low variance. This incentivizes low variance in reconstruction. And I started off here incentivizing low variance in reconstruction, but I ended up getting a loss function of loss beta-VAE, where you have a beta term corresponding to the KL divergence. So now if beta is small, the KL divergence is less optimized. Right? You don't optimize the KL divergence, which means you say that, okay, I concentrate more on reconstruction, less on regularization. If this goes to extreme, extreme, that is beta goes to 0, beta is equal to 0, right? Then x minus m theta of z is just the objective, which means I have no generation ability, no generation. This is the dilemma, right? I have no generation ability because I have not, now I cannot sample from z in normal 0, 1, I cannot, and expect it to go through m theta and get an output which is distributed in terms of p theta of x or p of x. I will never get that. Right? Because I have not sent the distributions close to normal 0, 1 so that I can sample from a distribution so that the decoder can decode it. Similarly, if beta is large, all the distributions, all the latent distributions collapse to normal 0, 1 and become independent of x of input, making reconstruction poor. So if it is too large, even generation can be poor. If it is too large, generation can be poor too. Poor as what would happen? As your output, so because your decoder, as your decoder has to reconstruct from latents, which has very little information about data, which means that was in words, which means that q phi of z given x almost becomes equal to q phi of z, which is independent of input. So if you have no features about the input, clearly our generative model is this, where we are sampling a z and we get a data sample. So if they are independent, I can never sample. So if you have too large beta or too small beta, you both of ways, you will never be able to either generate one beta too large will make the everything normal 0, 1 and you will not be able to reconstruct for that. If you have beta to be too small, you will never be able to generate data again because the distribution will be far away from normal 0, 1. So if you have a timeline, a hyperparameter line here, beta equal to 0 and beta equal to infinity. So here at this end, it is just an autoencoder. Encoder, no generation, perfect reconstruction. At this end, everything collapses to normal 0, 1. Again, poor generation and reconstruction. So you have, so I will just maybe write it down more clearly. So these here, you have these features. autoencoder, no generation, perfect reconstruction. At this end, you have collapse to normal 0, 1, Q5 of Z given X independent of the data, no generation, again, will be blurry. So you will not have no generation, you will have poor generation. That's the difference, poor generation. Because it will be blurry, average of, it will become blurry because it will, all features of all classes of data will average out. And therefore you will see the average of the MNIST, some data like this, some averaging like this in between. So you'll see something like this because all the digits are in the center. So features of all the classes will merge and you'll get a blurry generation. Somewhere in the middle, you will have okay reconstruction, okay generation, or rather we say good reconstruction and good generation. And perfect clustering of classes. We'll see what does this mean. This is because it will give you such a distribution that it will look like normal 0, 1. You will be able to sample good generation. So this is the beta optimal, where you will get good reconstruction, good generation. And you will also get what is called as clustering ability of the model, because it will say that some Z's look like more like 1, as I was saying. So if you see the representations here, as we were discussing here. So something like this, let us consider what do I mean by clustering? Say if I have zeros to be like this, ones to be like this, twos to be like this, and so on. And your normal zeros distribution is like this. And somehow this total distribution balances out. So you will see that the zeros are clustered, ones are clustered, twos are clustered. Although I have not given any label information, automatically the model will cluster this, just like a GMM would. We discussed in the first class how a GMM would by taking multiple Gaussian models. Here, what would happen is the model would build the nonlinearities in such a way that it will cluster data points within the normal 0, 1 distribution so that Q5 of Z given X is not equal to Q5 of Z. So it has maximum information about the Z remaining in it and still is able to cluster. Now, so this was all hand wavy by setting beta. Right? So we set the term beta and we saw that we'll implement this and we'll show you how this works. For MNIST, it will work perfectly fine. But as you can see, there's this antagonistic forces that is coming in. As I'm increasing the KL divergence weightage, the models are collapsing. As I'm increasing the reconstruction weightage, the models, what is happening to the model is becoming so separated out that I am not able to reconstruct at all because there's no KL divergence, which is going to make it like mu and sigma, which is like mu 0, 1. Right? Normal 0, 1. It will never become like normal 0, 1 is what we saw. Because this becomes an autoencoder at the end of the day where there's no reconstruction term. So what the model would do is it will separate out, say, class 1 here, class 2 here, and you have normal 0, 1 here. So the decoder will never be able to decode anything. That's the idea. So now to explicitly force the latent. So I was showing if beta was small. So now we are going to what is called as the info-VAE. And the entire the stem. So beta-VAE, info-VAE just brings in the idea of what is lacking in beta-VAE. That is, in beta-VAE, we want maximum reconstruction. Right? I want maximum reconstruction to be available to me. It should be in my hand. I want, but what would happen is, and I want it to mimic normal 0, 1 as closely as possible. Right? So we want to mimic normal 0, 1 as closely as possible. Here, this is where this problem arises that q phi of z almost becomes independent of the input, may become independent of input, and decrease our ability for generation and reconstruction. So these two problems, the second problem is what influences the info-VAE to come in. So the info-VAE says that L info-VAE says that, okay, I will have the beta-VAE loss and I will add a loss that maximizes information of X in Z. So I'm saying since the scale divergence term is forcing the information of less information of X in Z because the distributions are coming close to one another, I'm saying that I will add an extra term in the loss objective, which will maximize the information, which will compensate for the loss of information in Z. So it becomes, so we don't want this lossy compression. This is what is happening is a lossy compression, right? So VAE is going to a bottleneck. And while going to the bottleneck, we are having this compression. This is like any JPEG image or something, which gives you lossy compression. So here I'm saying that minimize the loss in compression. Minimize loss in compression. Okay, so now this is the idea. So I will say that I will have the beta-VAE objective, all right, but I will also have another objective, which will say that I can have enough information of X in Z so that I can reconstruct, as well as when I'm generating, I get very, very crisp images. And it gives you better clustering so that you can do it for a multiple downstream tasks. So if you have this separated out well, you can always have a classifier which will predict which class. So these are called downstream tasks. So downstream tasks can be better if there is maximum information of X in Z. So again, everything, if you club together of the last few days, what you actually end up knowing is, so you want the latent to have maximum information about X, about the data, so that the latent is actually separating out the data in some representation space, which helps you in classification of multiple tasks. Could be digit classification, could be object recognition, and so on. Because it is low dimensional, it is easy to train classifiers on those to supervised learning. And it is going to, in a generative sense, also it's going to give you better generation, right? So everything, all of these will hold up. So anytime you think why the VAE works, you should think of that bottleneck forces it to learn representation in the low dimensional manifold, which is the manifold hypothesis, that structured data is always resides in a very, very low dimensional manifold, right? So just give me a moment. Okay, so now what will I do? I'll do something. Let us understand how will I, but how do I maximize information of X in Z? So this is where another information theory term comes in. The information theory term is called the mutual information. So what is mutual information? I of X comma Y, if X and Y are random variables under a distribution P, it is given by the entropy of X minus the conditional entropy of X given Y, which is the same as the entropy of Y minus the conditional entropy of Y given X. This is symmetric. So you can equate these two and you can see clearly that your entropies, so what you would end up having is, so this entropy, you could show why it is symmetric. Can you tell me why it is symmetric? So this is symmetric because the entropy, as you all know, is defined as P. The integral for a continuous distribution is P log P. This is called the differential entropy because it's on distributions. On a discrete distribution, it's minus P, or x equal to k equal to 1 to, if there are capital K classes, log P of x equal to k. Right? This is the for a discrete case. Discrete. This is continuous analog. So I will write integrals so that we don't have to deal with summations, and because integrals are easy to put, and I'll throughout. And whenever you have implementing when you will implement these algorithms, they will all be discrete mostly. So you'll be able to implement them as summations when you have expectations and things like that. We'll prevent a lot of summations and PMFs where I have to set the value of the random variable. What I'll do is I'll just put integrals to minimize the writing time. So this is entropy of x. What is entropy of x given y? This is nothing but P of xy. This is the joint distribution under the joint distribution of log of x given y. So the conditional distribution of x given y, right? So this is what is known as x given y. So what you can write this as is P of xy, x comma y, log of pxy, P of xy by P of y. Just using conditional probability rules, and you have two integrals here, dy dx. So now you have a joint entropy of x comma y, right? So this term is a joint entropy, and you have a minus a entropy of y, because in the second term, so if you're not following, I'll be doing this multiple times in today's session. I will marginalize one variable out if it is not there. So this internal logarithm does not have x. So I can marginalize x out from this, and I can just write this as log p theta of y integral of p xy dx dy. So this will be p of y log of p theta of y, which is nothing but my negative entropy of y, right? Good. So this is, you can see, which therefore our likelihoods this becomes equal to, if I use the expression, so conditional entropy becomes h of x plus this value for the conditional entropy. You can see that it's a joint. You can replace x and y. It's a symmetric term, right? So now this is very, very interesting to see such a beautiful equation. Why? Because this can be interpreted in multiple ways. Interpretation. Why do I write this? Interpretation. The interpretation goes as follows. What do I interpret this as? Say first, say x comma y are independent. If x and y are independent, your mutual information x comma y clearly can be written as h of x minus h of x given y. So this is equal to h of x minus, again, I'll write down p of xy log of p of x given y dx dy. So this conditional distribution, what will it become? We know p of x given y is equal to p of x if x is independent with y. So I will make this p of x, right? Similarly, I will marginalize y out, y, and I'll get minus p of x log p of x dx. This is what I'll get, right? So which is equal to, what is this equal to? This term is equal to the entropy again, h of x, correct? So h of x. So again, there's a negative sign over here. Please be careful about that. I forgot to put that negative sign. And if I've not put it even before, so yeah, I forgot to put it here again. The negative sign here as well, I guess. Yes. So if I miss negative signs because of entropy is the negative of the integral, please bear with me and correct them. I'll not miss them, but I'll try. So here you get this is h of x minus h of x, which is 0. So x and y are independent, you get 0 as the mutual information, which is expected. If x and y are independent, you are not getting any information. So the idea to interpret is, so if you can see this entropy term, entropy is randomness. Entropy is randomness. It is the intuition. So high entropy means high randomness, right? So now if randomness decreases, right? So that's what that is. H of x minus decreases on knowing another random variable, right? So it's a difference between the entropies, how much entropy decreased, right? So if my random variable, so if two random variables are independent, you would have, there's no decrease. So you're saying this was your initial entropy, this is your final entropy. And since there's an inverted sign for entropy, that is high randomness means entropy being high, B is randomness is high, which means uncertainty is low. There's you have low, sorry, certainty is low. Uncertainty again would be very high if you have high entropy. So certainty is low. So you're saying that the final entropy, if the final entropy was, what do you say? If the final entropy was lesser, so you are subtracting this term. If final entropy decreased, right, than initial entropy, it means what would happen? Y has information about X, right? So your final entropy has decreased. You have become more and more certain. Randomness has decreased because Y has given some information about X. So which means that this term, if your final entropy decreases, your H of X minus H of X given Y will increase, which means mutual information would increase. That is, which means Y has info about X and vice versa, your mutual information increases. This is what I wanted to say is the intuition. Your final entropy is lower. So let's take a perfect case where X is equal to Y. If X is equal to Y, what is the conditional entropy of X given Y? Let us write this down for a discrete case. It's not defined for a continuous case. Let's write it out a discrete case. So it's P of X given K equal to K. Log of P of X equal to K given Y. Right? So this is, and sorry, this is the joint distribution, right? So conditional distributions are P of X equal to K and Y equal to J, right? Y equal to J, X equal to K and Y equal to J. And this is the summation that you have over all K and J's, right? So now I know if K equal to J, P of X equal to K, Y equal to J, right? What will this be? For k not equal to j, what will this be? P of x equal to j, y equal to j. What will this term be? So if you are not able to figure it out, we can always write this as a conditional distribution. Y equal to j into probability of y equal to j. Correct? Do you agree? This is equal to 0, right? If they are not equal, because I know x is equal to y. If x and k and j are not equal, the conditional distribution can never be. So we know what is the conditional distribution. Known that known y is equal to j, what is the probability x equal to k? What probability of x equal to k, right? So if they're not equal, and I have told that they're equal random variables, then this term is equal to 0. If this, let me write it. I've already written it above. So here 0. This term is 0. If they're equal, then I have p of x equal to j, y equal to j, given y equal to j, right? This is equal to 1 into p of y equal to j, isn't it? This is what I'll have. Very good. So now let us write down the summation. What will I have? I will have only where k equal to j, I will have probability of y equal to j into log of p of x is equal to j, y equal to j. So again, these terms are again equal to 1. So this is again log of 1 is equal to 0. So you can see x of x is equal to 0, which is what you expect, right? So x has complete information, has all information about x. So no entropy. So your mutual information is equal to h of x minus 0, which is h of x, which is the highest, right? This is the highest value that you can have. That's the idea. So it's a maximum. When x is equal to y, you exactly know everything about x in y, right? So the two things we learned, if x and y are equal, then we have entropy where the difference in the entropy is final and initial to be very, very high, which means that mutual information is very high. If they are independent, what you would end up having is you would end up having these to be the mutual information between them to be 0. Because what you'll see is there's no information about x and y. So now, as you may already understand what I'm trying to say, formalize if you are told to formalize. So what I want you to take away from info-VAE, because the next few 20-25 minutes will be just derivation of different forms of the elbow. I want you to, if you want to take away something from the info-VAE, it is this, that you want maximum information of x in z so that you can get best reconstruction, best clustering, best downstream tasks, everything. You get best of every world. So L info-VAE is equal to L beta-VAE plus some, say we are going to use alpha times, this is some hyperparameter which you can tune to get best numbers on a validation set, not DKL, sorry, alpha times the mutual information under the encoder between x and z. We want the encoder to output z's so that this x and z has maximum info, right? So let's try and write this down properly. Okay. Okay. So if you're wondering how will we write this down, so let us write this down as a single number. So let us write this down. What is KL divergence? First, let us write this down. KL divergence between P and Q distribution, right? Not KL divergence, sorry, mutual information. Mutual information between X and Y can be written as I said, P of X log Px dx minus P of xy log of Px given y dxy. So again, if you look at this, what do you see? So it is negative here and positive here because this is entropy of x minus entropy of x given y. So this term, what does it turn out to be? So see, I can always write integral of x and y and write this as p of xy log px dx plus integral of pxy log of p of x given y dx dy. See again, here I will be able to marginalize y out if required, and I get back the original entropy of x. So why did I write this? I write this as p of xy log of p of x given y by p of x dx dy. So now from this term, you directly see one thing. If p of x given y is equal to p of x log of px given y by px, this goes to 0. So this entire mutual information term goes to 0. This is another way of looking at things. So what can you look this at? You can look this at in this form. You can write this as p of xy log of pxy by px into py. This px given py, I wrote as conditional expectation of pxy by px py. And I get dx dy. So now people who have already done the previous two sessions already know this. This is the Kale divergence between pxy and px into py. Again, this is another interpretation. What is the distance between the distributions joint, that is one joint pxy and independent pxy is equal to px into py, and the independent distribution px into py. So if pxy joint, if joint goes to px into py, you have minimum. If joint, if independent, this will go to the product. So you are trying to say what is the maximum. You are trying to separate the joint, make the joint to be as far as away from the independent distribution of x and y. This is the intuition, another intuition. So now let us see what. So now the remaining half an hour, what I'll do is I'll do different forms of the elbow, and I'll show you what is the objective function of the info-VAE. So that's the objective of our next few 15-20 minutes. So let us first do for the first part of this. So let us do this. So instead of just writing the original VAE form, we will do another trick first. We'll do this trick before we write down any other form. So we'll say that the info-VAE says that the elbow has this form. Okay. The first thing is show that. So you can play around with the elbow and show you can create multiple representations of the elbow. And each of them have a different idea. So each of them would give you a different interpretation. Show that the elbow can be written as this. So let us write this elbow down. So now we know what is the elbow, right? We know the elbow if theta and phi. This is given by P of, if you want to write down the elbow, this is what is the elbow distribution? Log of P theta of x comma z by q phi of z given x. This is the expected value of under the q phi distribution, right? If I do not write the entire thing, and we have an expectation over the data points. This is what we know. We want to, this is known as the elbow. We know that this is lesser than the likelihood of the data, right? Where this is the variational distribution. So now I'm saying instead of writing the original P theta of x given z minus dkl of q phi of z given x and P theta of z, I want a different form. I want to match the marginals of the data and the encoder and the latents. Let's see, what does it mean? So I am saying I have these assumptions. I have assumption 1 as q phi of z, that is the marginal of the latents under the encoder model or the variational model. These are the assumptions. This is equal to the integral of, what can you write this as? Q phi of z given x into q phi of x dx over all the data points. Now I tell you that I don't want to model the distribution of the encoded data because I already know so what I'm doing is already p theta of x is modeling px. So I will not model this distribution. I will say that this is equal to the data distribution. I will say I'm not going to model this. I will say this is equal to the data distribution. Data. So I will say that my q phi of z is equal to the integral of q phi of z given x px dx. And you can do Monte Carlo sampling to get the value, right? The px. So this is again x sampled from px. Can just sum over 1 by n. Q phi of z given x will give you the I equal to 1 to n. So this is just Monte Carlo sampling, but based on samples. Because it's just the expected value of the q phi of z given x under the data distribution. Okay, so let us write this down in this form now. So we want this to be the expected value of px q phi of, so let us first write down the double integral over here. This is p over x px q phi of z given x. Sorry. So I'm just writing both the integrals down. This is over x, this is over z. And I have log of p theta of x given z by q phi of x given z into q phi of z by px. I'm just using Bayes rule. I'm making x and y to be conditioning on z and getting the posterior on x. The numerator term just becomes p theta of z, right? Because I'm just using conditional probabilities there. Okay, so as soon as I do this, what can I do? So this p of x, I can write in the numerator as px, and I get this terms out, right? So now I will factorize two terms over here. I will factorize this term out, and I'll factorize this term out. And this does not depend on data. I'm wrong by saying they don't depend on data. Independent of parameters. So let us see when they are independent of parameters, what will this become? It becomes px q phi of this type of things I'll be giving in your assignments. And you'll be able to understand that how the elbow can be you can play around with it. That's all you'll be doing in generative models throughout. We'll be doing even in diffusion models and so on, right? So this you can see again, z in this case, neither this term nor this term depends on z. So I can integrate out z. So I can just integrate q phi of z given x dz. And this is equal to 1. This is equal to just 1. Because there is a law of total probability. And you'll get integral of px log px dx. So this is the negative of the entropy of x. And this does not depend on no model parameters. Does not depend on model. On theta or phi. So I don't need to optimize this. So I will say that I will write this as plus some constant, which is independent of the parameters theta and phi. This term over here, I can write this as, what can I write this as? I can write this as px, right? If I multiply these two, I will get q phi of x comma z, the joint distribution, right? Once I get the joint distribution, I can write this as q phi of x comma z. I get the, okay, I'll use different boxes to maybe represent this, then it'll be easy for you. Right, so the blue box over here, I can write this, the first blue box, in form of minus, I will just invert whatever I have, log q phi of z p theta of z dx dz. Right, I'll separate the derivation from the notes. Okay, so now what would end up happening? This is equal to, now you can see I can marginalize x out, marginalize x. So I get q phi of z log of q phi of z p theta of z dz. Okay, so people who have been following me, this is nothing but the KL divergence, negative of the KL divergence of q phi of z and p theta of z. So this blue term becomes this, right? Now the green term, this is the blue term. Now the green term will be the integral of q phi of x comma z, x and z, log of p theta of x given z, that is the reconstruction of the data, and the posterior of the variational distribution, dx dz, right? This is the green term that I have. So this term again, see, I want to write a KL divergence again. So what will I do? I will write this as, okay, I'll not use the same colors. I'll write this as q phi of x given z into q phi of z. Clear? As soon as I do this, I can write down this as q phi of z integral of, this is over z, the integral is over z, this is integral over x, q phi of x given z for negative sign, log of q phi of x given z and p theta of x given z dx dz. Again, clearly this term is the KL divergence, and you have an expectation over the z sampled from q phi distribution. So you get the DKL divergence between q phi of x given z and p theta of x given z. So this is what I was trying to prove, right? X given z and so on. So if this is over the distribution of z and not the conditional distribution, so marginal. So now I have proved, we have shown f theta and phi is given by minus of the DKL divergence between z and the p of z, q phi of z and p of z, which is normal 0, 1 again, minus the KL divergence between, or the expected value of KL divergence between q phi of the posterior of the data distribution given the latents and the reconstruction data of the data, right? These two terms is what we have. So what is the interpretation? This is, so we say that this is A and this is B, and our info-VAE says, L info-VAE to be exact, is going to tell me that A plus or minus A minus lambda B plus alpha times x comma z. So we have understood the interpretation of this, maximize MI for mutual information. These two terms means you are matching q phi of z to be equal to normal 0, 1. That's what we want. Even at the marginal space, even marginals are matched. Marginals are matched. And reconstructions are matched. Across encoder decoder. So this is, and when you give different weightages to this corresponding losses, you can really play around with the reconstruction as well as the marginal. Remember, in the original VAE, all the reconstruction, all the marginal terms were being calculated. You did not do it for a distribution. You were just doing a likelihood there. You did not explicitly match the encoder and the decoder. You took samples from the encoder and marginalize the reconstruction and decrease the reconstruction for the decoder. Here you're saying the distribution for the encoder and decoder should be the same, as well as the marginals should match. In the original, q phi of z given x was equal to q of normal 0, 1. It is vanilla. In this one, you're saying it is more likely to match at the marginal level. That is, if you integrate out x, it will match. And whatever information of z x contains will be captured in the mutual information. Capture info of x in z. It will capture, right? So you're doing three things. Match marginal. This is the beauty of the info-VAE. Match posteriors, better reconstruction. That is of data given latents. Latents under both the encoder space, under the encoder and decoder. For both, not under, for both encoder and decoder. So you make them talk, make them match the same objective. That is, you're making both the encoder and decoder give you better reconstruction, better recon. This will give you better marginal, means better closeness to normal 0, 1. And the third term, the information, mutual information, maximum information, will maximize the information info of x in z. Okay, so these are the three objectives of the three losses, right? This is for A, this is for B, and this is for mutual MI. Okay, so now with that, let us write down what is the objective going to be. We will start from this objective and we'll see this is not interpretable because this term has not been implemented by us. We have not implemented an encoder which takes in latents and gives you the data. So we'll have to find out a distribution, find out an implementable form. So let's tell this equation to be dagger. Dagger is not implementable as q phi of z given x is not a neural network. So we'll have to do something about it. So what do we do? So we'll do something. We will try to have another term here. So if you see, we will show that this equals a normal VAE with different weights and an extra term. That's what we will show. I'll copy the equivalent condition, what is equivalent objective of the info-VAE. Okay. So we want to show that L info-VAE equal to minus DKL of q phi of z given x, pz, no, not z given x, sorry, DKL or expected value of lambda times the expected value of q phi of z, DKL of q phi of x given z, p theta of x given z, plus alpha times the mutual information between x and z to be equal to this term. You have a reconstruction. This is reconstruction This is regularization. So term 1 and 2 is the beta-VAE objective, which can be implemented, which we'll implement today. And the term 3 we will see. Will be a, this is marginal matching. And how we'll implement this, as I'll tell you at the end after I derive the objective. So let us see. So it turns out to be a beta-VAE plus marginal matching. So info-VAE can be thought of as beta-VAE plus marginal matching. Okay, so now let us, so first term that we have over here, q phi of z given x and p theta of z is already implemented, right? Let me just check, where do I have the lambda once? And then we have lambda for the first term. Okay. Just a choice of where you want to put the lambda, right? You want to put lambda in the first term and the second is beta. Okay. So lambda is in the first term. So first term is okay. We don't have to do anything about the first term, right? Because first term is already there in the final objective. So when you're proving something, you always see what you have in the final objective. So this term is already there. So I don't need to do anything about this term. What I need to do is I need to optimize this term and this term. So let us look at the mutual information term first. I want to break down mutual information term into the first any of the three terms, right? So how do we do that? So we know that the mutual information is q phi of x comma z, the joint distribution, and x given z by q phi of dx dz. Or I can write this as the joint, as the Kehl divergence into interpretation. And I can write this as px q phi of z, isn't it? So as soon as I do this, you can see I want q phi's to not condition. We don't want q phi to be conditioned on z. We want it to be conditioned on q phi of z given x instead of x given z, right? So what will I do? As you can clearly understand, this will become, so let us keep out the alpha for the time being. This will clearly become q phi of, I'll just easily write this down, q phi of z given x, p of x, because we have already thought of this factorization, that q phi of x is not being modeled by s, log of q phi of, again, z given x into px q phi of z dx dz. Okay, I will cancel these two out. Very good. Now I have very nice terms coming in for me. Now you tell me, now I want it to be in Kehl divergence of these terms, right? So if I want Kehl divergence of this terms and this terms, what will I do? Term 2 and 3. Very simple, isn't it? I will just multiply and divide by p theta of z. If I multiply and divide by p theta of z, instantly what you get is, see, there's two terms you'll get. Integral over z, q phi of z given x, and I put px outside for purposes you'll soon see outside, z given x, p theta of z. So I will club these two and I'll say this is dz dx, and I will have one more term that is plus integral of q phi of, I am putting these two together now, q phi of z given x log of p theta of, or I'll put a minus here, and you can just write it in one go, q phi of, this is really just rearranging the algebra, q phi of z dx dz. So as soon as I do this, I marginalize x out. This is x and z, marginalize. This is the second term becomes very simple, q phi of z log q phi of z p theta of z dx dz. Now again, as soon as you see that, you will tell me, okay, I can clearly see that this is the negative of the Kehl divergence of q phi of z and p theta of z. So clearly I can see that I have got term 3. Term 3, in terms of term 3, this is our weight of term 3. I have a term 3 here. And this term, clearly again, you can see you have an expectation of over px, and this term is a KL divergence. dKL between q phi of z given x and p theta of z. Right? This is term 2. So now from the mutual information alpha times iq of x comma z, I have shown that it is equal to alpha times the expected value of px dKL q phi of z given x with the prior term, that is normal 0, 1, p of z. Whenever I write p theta, remember that p theta of z is equal to p of z, which is our choice, right? Minus the dKL term alpha times q phi of z p of z. Okay. So I have written it in terms of this is alpha times term 2 minus alpha times term 3. Very good. Now the second, so I have been able to factorize the mutual information term in form of the final equation terms. And I have to factorize the second term over here, which is the posteriors of the encoder and the reconstruction of the decoder. So let us try to do that. So what is that term? We have, this is the second term. This is, I'll put a sign over here. Maybe I'll put star or double star. So double star is dKL of, what is it? Q phi of x given z and p theta of x given z. So all I want is I want p of it to be in this term should not be there. It should be all in terms of z given x for the encoder and x given z for the decoder. Q phi. Okay. So let us write this down. So it is q phi of z. This is over z and this is over x. Q phi of x given z log of q phi of x given z p theta of x given z, right? So I don't want anything much from the term on the denominator because I want that to be the reconstruction term. So what I do is the numerator I will be factoring out. So what will I do? Again, x and z, I can write this using Bayes rule as q phi of z given x. So this is the joint q phi of x comma z and into px. So again, just using Bayes rule, I just recalibrate it as this form. And the inner sum, again using Bayes rule, I can write this as q phi of z given x into px by q phi of z. Very nice. And p theta of x given z. Okay. Now, as soon as I see this, see there will be a term. This term will be there with me. But I don't want that term. What do I want? See, first, this terms. When I separate out px, this will give me a constant, right? Because I will write this as log px integral of some q phi of z given x, px dz dx. This goes to 1 and you get entropy of x or some negative of entropy of x, right? So I can say that I will be dropping out this term. And I will, because I am putting a constant is independent of theta and phi. By now you must have understood that. Okay, so now again, I will have to play a trick. I have to multiply and divide by z because I want those terms to exist in the final equation. So as soon as I do this, now you will tell me, yes, now I see the terms that I need. What are the terms that I need? I need these two terms, right? Not this, sorry. I need this term, which is there in a vanilla VAE, right? I will just maybe rewrite this very little bit more clearly. X and z, q phi of z given x, px log of q phi of z given x, p theta of z, which can be written as p of z, into p theta of x given z. See, all the terms are coming slowly, and you will have p theta of z or p of z by q phi of z. So clearly you can see this is term 1. Rather, this is term 2. This will give rise to term 2. This will give rise to term 1 in the original equation. This will give rise to term 3. If you're following me, this is exactly what I want. So this is equal to, what do I get? See, the first term that I have over here depends on x. So I'll get p of x integral of q phi of z given x log of q phi of z given x by pz. This is my first term. Again, as soon as you see this, you know what is the first term. This is my term with the red block. Again, I'm putting the same red with a dagger over here, with a shade over here. And this first term becomes equal to the expected value over px log the DKL divergence between q phi of z given x and p of z, exactly the term that we needed. The second term, as you can see, is an expectation over the data point x's. So this is minus, because it is in the negative, over x px q phi of z given x log of p theta of x given z. This is my green term. And this becomes equal to minus the expected value of px log of, we have expected value over px and z sampled from q phi of z given x and log of p theta of x given z. That's the reconstruction term we knew from VAEs. And the third term over here, the blue that I have, I can write this as the integral of q phi of z, because x will be marginalized out, because this term is independent of x, log, and you have a negative sign again, q phi of z given x, p theta of z or p of z, pz, which is equal to the DKL term between q, the matching term, and p theta or p of z. Very good. So now I have 3 terms over here. This is negative again. So now let us collect all the terms. Let us collect all the terms. Okay. So how do we collect the terms? We have, so our lambda times a, or minus lambda times a minus b plus alpha times iq L info is equal to lambda times a. Let us write this down. Minus lambda, a was dkl. Just remember, a term, I didn't have to do anything. This was the first term, my prior matching term. DKL between, or marginal matching term, p theta, whenever I write theta, please, this is fixed. Minus b, b is, second term is what we just factorized out. It contains of minus the expected value over x, the expected value of z sampled from q phi of z given x, log of p theta of x given z, plus, right, DKL between q phi of z given x, p of z, right? And we have one more term, I guess. This term. So the third, so this is, I will just put down boxes so that you can understand what terms have we. So these are the 3 terms that I have in the correspondingly 3 terms, right? So now I will write this as minus DKL of q phi of z, p of z, right? And I have the mutual information term plus alpha times, what is it? Alpha times the KL divergence, the DKL of course, over x, px over the distribution of x, q phi of z given x, and p of z, right? This term, and I have a prior matching term. That is, both were negative, I guess, I think. Second term is negative, first term is positive. Okay. Negative of dkl of q phi of z given x, or rather q phi of z, sorry, and p of z. So let us now collect all the terms. What do we get? So we get the first term, which is this reconstruction term. We get expected value of px, expected value of q phi of z given x, right? Almost done. Log p theta of x given z. So first term is done. Second term, how many terms do we have for the second term? We have this term, star, and we have another star here. So we have alpha is positive, and this is negative. So we can write negative of 1 minus alpha dkl q phi of z given x, p of z. Okay, and the third term is the prior matching term, which can be written as plus this term, and this term. So lambda is negative, alpha is negative, and lambda is negative, alpha is negative, and this term is positive. So I have 1 minus alpha minus lambda, or I can write this as alpha plus lambda minus 1. Put a negative sign over here. Expected value of q phi of z given p of z. Okay. So what is the, I think, the objective? Okay, that is right. So now you see, I know if I write this as 1 and this as 2, 1 and 2 implement as beta-VAE. 3, we will see, can be implemented as adversarial networks, using adversarial networks. What does it mean? We'll see in GANs what does it mean. But the idea is, I know q phi of z is, by Monte Carlo sampling, is similar to n equal to 1 to n q phi of z given x size, right? So what I can do is, I can do this across a batch, and I can minimize the mutual information or the KL divergence. So the KL divergence, right? I can get the sample average and I can minimize the KL divergence. This is one objective, or one way I can do that, and then minimize between P of Z. This is way one, or take Z from Q phi of Z, right? Z from normal 0, 1. That is, you'll get Zs by just averaging this, right? You'll get Zs from just by averaging these. You can sample average the Zs, and then you use what is called adversarially align the distributions. Align distributions of Z and Z tilde. It will become more clear when we do adversarial learning or GANs. So by the time being, you know that using adversarial learning or by using sampling to estimate the Z over a batch, you can minimize the distance. So when you do adversarial learning, you'll be seeing that how I can get Zs from Q phi of Z, and I can get always sample from normal 0, 1, and I can get a discriminator. The discriminator will say if from encoder or from normal 0, 1. If the encoder, if discriminator is not able to say, then we have aligned the representations. And we'll have to design algorithms. We will have to design algorithms to ensure that discriminator is not able to distinguish. Let's see, we'll do it when we learn about adversarial networks. With that, we come to end of the theory part of today's session. We have learned everything about VAEs, the state of the art info-VAE, beta-VAEs, and also we know the objective function. So what I'll do now is I'll stop sharing from my tablet and I'll show you the code for a VAE, I have implemented that code, and I'll show you how a VAE can be used for multiple purposes, for generation, for reconstruction, for bottom downstream tasks, like where you will be able to use it for clustering, right? Let's do that. Okay. Sorry. Okay, so I'll share from my laptop and I'll show you the code. Okay, I hope you can see the code. So we'll be using TensorFlow in our coding, and you can download the code, and when the assignments use them for various work. So what I've done here is, here I have imported a bunch of libraries to define a layer, to define the optimal, to define the VAE. Next, what I do is I select GPUs on which I want to run, and then I load the MNIST dataset. The MNIST dataset has around 60,000 samples in the training data. I'll not run it here. It takes a while, 30-40 minutes on fast GPUs to run. So I'll show you the trained model and how you can use it for inference, and I'll show you the code for it, right? So what you can do is, take this training data and you see how the MNIST dataset looks. So MNIST dataset is looking like this. So what I want to do is I want to be able to generate handwritten digits. So let's see how the beta-VAE class looks. So you can forget about load and save methods. You can see them, how I have implemented them and plotting curves. So I have implemented an encoder. What is the encoder going to do? I have simply a convolutional neural network as the, so I will show you the, maybe I'll just show you what the, okay, this is not, okay. So if you see the encoder here, what I have done, sorry, I have, draw shapes. Is it not loading? Yeah. So how I have implemented the encoder is, I have a shape. Okay, this should be a trapezium. I'll try to import it from. Okay, I'll just try to draw it over here. So I'll have an encoder like this. And this encoder has a bunch of convolutional networks. So I have a 3x3 filter that takes in the image. So I have, say this, I'll just erase this. So I have this input image that I have over here, say a 7. And then I pass it through a convnet. So this convolution network, as you know from my previous courses, is just to take convolutions. Here I will have layer 1 conv. I will have layer 2 conv. I'll do max pooling. And I'll do conv 2. And I'll do conv 3. And I'll get what as around, if I see just a moment, you can see the data. If you see the model output, I'll get a latent dimension of 256. I'll flatten it and I'll get a latent dimension of 256, actually 32. And then I'll use a linear layer to make it 32 dimensional. Okay, so I'll do conv 3. I'll get flatten the vector, output it, and I'll get a 32 dimensional latent. This is mu of x and sigma square of x. Right, I will mu of x and log of sigma square of x is what I'm implementing. These two models I'll implement as I have shown last time, because we want the VAE not to be, the encoders not to be constrained to give outputs between 0 and 1, between 0 and infinity, because sigma cannot be negative. So we model the log of sigma, which is a real number. Then what we do is we pass it back to 256 dimensional data. We do what is called as upsampling. Upsampling as in if you have a 1, if you upsample 2 times, it will become along x and y, it will become 1, 1, 1, 1. So this is how you do upsampling. So from lower vector, you pass it through a larger vector. This is the decoder. You make it a higher dimensional data, and a higher dimensional. You have a conv then. You have a conv layer, and you go on doing it till 28 cross 28 is the output, which is the input data, so input. Okay, so this is the entire idea of the architecture. So let's see what I have done. So you can see that I take, this is the input channel. I pass it through a convolutional network with filter 3 cross 3. So what it will do is it will do 3 cross 3 convolutions, and then it will have 4 outputs. So the output layer will have 28. So from 28 cross 28 cross 1, it will transfer it to 28 cross 28 cross 3 cross 3. And then we'll do max pooling. So every 2, I'm going to take the max value of the 2 values. I hope you know that's the prerequisite of the architecture, the prerequisite. So I'll miss 28 along every dimension. I'll just take the maximum value for a 2 by 2 filter. And this will become 14 by 14. And I'm padding for all those who are thinking that why the dimension did not decrease on convolution. So I'm padding to keep the dimension same, 3. So and this is going to continue till I reach 7 cross or 4 cross 4 cross. Just one moment. Yeah. So this will give me an output of 4 cross 4 cross 16. Because I have 16 channels in the final output, I'll flatten them. So I'll get a 256 dimensional vector. And this 256 dimensional vector will be passed through a dense layer, and I'll get a 32 dimensional. So I've reduced the 784 dimensional MNIST dataset to a 32 dimensional latent of mu and sigma. And then I take this input of the encoder. So I take the decoder input. Now I pass it to make it 256 again. I reshape it to 4416 and I do the deconvolutions. That is upsampling and conv2d. Upsampling, conv2d, and output will be 28 cross 28 cross 2 or 3 cross 1. 28, 28, 1. Okay, so this is how you make the model. So now let us see what is the loss function of the model. So you have the encoder and the decoder. So the loss of the VAE is very simple. You get a noise term. You pass the batch of inputs and the noise, and the model gives you the reconstruction, right? So reconstruction loss is just the MSE loss. Now you pass it through the encoder, pass the batch to the encoder. So this is the reconstruction term in the so you know that VAE has recon plus minus KL. Beta times KL. So here we are minimizing. So I may write minus recon and plus KL. So if you are thinking if there are signs, so we are minimizing. Okay. Okay. So minus recon is, if you're thinking what is minus recon is minimizing MSE. Okay, so now I pass it through the encoder. The encoder gives me mu and sigma. And once I get mu and sigma, this is log sigma. So I take the expected, I put it exponent of, so x is equal to exp of log of x, right? This is what I do. And then I set the VAE, what is the KL divergence between normal 0, 1 and the mu sigma term. We have already found this in the class. That's what I do. And how is the model generating or reconstructing? It is taking in the input. It is passing it through the encoder that we have defined using mu and sigma. It is defining a noise as an input parameter. And this is a cute way of coding the thing where you have a lambda layer, where the lambda layer is going to say that it is mu. It is going to take inputs as mu and sigma. And I would have the input of the noise as well. So this is the noise. 1 is the noise, 0 is the mu, and 2 is the sigma. So I will just do x plus mu sigma, and that will give me the latent. And once I get the latent, I'll pass it to the decoder to get the reconstruction term. And the entire thing I say is a VAE, right? And then in the back propagation, what I do, I get the reconstruction loss, so the regularization loss, and I append then like a beta-VAE, and then just do, you can use this. So this is called a gradient tape. So any function that you write within the gradient tape in TensorFlow keeps gradients. And once you keeps ability to take gradients. So once you take the gradient, you can optimize the gradient descent algorithm and update the parameters. So the training model is just creating batches and training it. And we'll see how the model has trained. So this is the model training. This is the reconstruction loss. This is the regularization loss for beta value equal to, I'll show you the beta value. The beta equal to 0.10 to the power minus 3. Okay. Now for 10 to the power minus 2 also, we had trained a similar model. Now I will show how the reconstructions are. So let's load down the model of 10 to the power minus 3 and see how the reconstruction looks. So I will load some test samples. This is done on the test set, not on the training set. You can say it's overfitting. And then please look at the code once you look at it and try to play around with it with different betas, train the model and just see how the, so this is the original data and this is the reconstructed data. You can clearly see how the original and the reconstructed looks. So if you clearly see in the paper also, I was in the notes also, I was telling if you have an optimal beta, so 10 to the power minus 3 is an optimal beta, so it's giving you good reconstructions. Why am I saying it's an optimal beta? Let's take a larger beta, 10 to the power minus 2, for example. And if I do that, you can see, as I was saying, all of them goes towards independent towards normal 0-1 distribution. And the model decoder is completely confused and is not able to decode. So it's all the distributions have converged. So it's not a good beta value because all this q of phi of z given x have converged to q of z, which makes them independent of the input. Okay, so let us see the generation only for 10 to the power minus 3 then. We'll sample a bit of, so I'll show you the generation code. How are we generating? So we we sample latents and then pass it through the decoder, right? This is all we do. And then you can see the generation. These are automatically generated novel features generated by the data, and you can see the generation quality is really very high. But if you see the generation, I will write down the code for generation of 10 to the power minus 2. You will see how bad is the generation because the model, the decoder will be confused on which one. It has never learned to create anything from separated latents. It has learned only to create smudged images like this. So you will see when the generation becomes bad. So it's 0.01. See, the generation becomes really, really poor. Now, what I can do is I can pass this through the latents. The model has encoding capacity is what I told you. So say we have encoded the latents through the encoder and see if there is a list of downstream tasks it can do. And so that what I can do is I will use only the 10 to the power minus 3 wala latent, and I will do something called to do dimensionality reduction. I will get say 50 points or 500 points for every sample. And then I will do what is called, I will encode the latents. I got 32 dimensional for every data point. And now I will do what is called as dimensionality reduction to visualize it. I will do either a t-SNE or a PCA. PCA is, as you have studied in previous classes, keeps the maximum variance components. And I'll see if in the low dimensional space, they are separable. So let us see the PCA features of the digits. Somewhat, see, zeros are somewhere here, ones are somewhere here, nines are somewhere here. In the t-SNE space, you can see there is clear separability in the PCA space. But we know that PCA does not give you separability in the clustering space. It not the variance, it maximizes the variance, of course, variance explained, but it does not give you maximum separability. It's just a linear map in terms of the characteristics of the features, of high level features. For that, what people generally do is for better understanding the lower dimensional representation in terms of non-linear functions, we do what is called as t-SNE optimization. In t-SNE, what you do is you use a student t distribution to see which 2 points are similar to one another. And here you can clearly see that in the data, if you're not just trying to use maximize variance, you'll clearly see. Okay, I think I have changed. So we'll have to, I think we used the later one. Just give me a moment. Is it, or is it? Just give me a moment, get in. Beta-VAE, I have loaded the worst VAE. Remember this, so I'll have to rerun. So this is a problem in Jupyter Notebook. Once you reload, you cannot really do things properly. So let's look at it once again. This is the PCA. In the PCA space, you can clearly see separation. But in t-SNE, you will now see, in t-SNE, you were not seeing separation, which means there were not separation before in the lower dimensional when the beta was very high, which was showing that everything collapsed to normal 0, 1. But now you will see the magic. For the good VAE, the t-SNE is running. And it gives you. Why is it not loading? Just give me a moment to check. This is beta-VAE, beta-VAE.load. Beta-VAE.encode. Yeah, I think this will work now. This is the problem with Jupyter. Yeah, you can clearly see that for the right VAE with 10 to the power -3, you have the ones here, the zeros, nines here, the grays indicate sevens here, the zeros here, and the sixes here, and the threes here, completely separated out. Now, if you have just a linear classifier on this two-dimensional space, you'll be able to categorize between the digits. So powerful. So it means that the beta-VAE has really separated out the representations of each of the data. Although you have not trained, it is able to, overall, it has learned it to be close to normal 0, 1. It has been able to separate out zeros and ones, that the conditional distributions are separated. The marginals have been matched, and we have been able to generate and reconstruct. So we have been able to generate because we have been able to reconstruct because our conditional distributions are separated out. We are able to generate well because the marginals have been matched. And we have been able to have maximum information in the latents because the separability between X and Z's are very high. So we did not use an info-VAE, but we already have the maximum information about Z in X, which shows that you can clearly use this for MNIST, but for more complex data sets, you may have to maximize the mutual information. So with that, I'll just stop today's session. If you have questions, please feel free to comment them on the Teams channel. We'll discuss them in the doubt clearing session. Okay, see you.